Now this is the final video on chemical bonding in A-level syllabus. We have come a long way from discussing like the fundamental types of bonds. We have metallic bonds, ionic bonds, covalent bonds, and the factors that affect the strength of these bonds. And then we went on to look at intermolecular forces. And in order for us to discuss the factors that affect the strength of intermolecular forces, we had to learn many new things along the way. We had to learn how to draw the dot and cross diagrams for complicated molecules. From there we can determine the Lewis structure, the shape and bond angles, and from the shape therefore determine whether the molecule is polar or non-polar. So at this point we are ready to discuss the different types of intermolecular forces that exist, and then go on to look at the factors that affect the strength of the different intermolecular forces. We have seen in the last video that molecules can be polar or non-polar. Polar molecules have a net dipole moment. Non-polar molecules have a zero net dipole moment. So right now we're going to look at the different types of attractions that exist between polar and non-polar molecules. So we'll start with non-polar. So imagine you have a chlorine molecule. So the chlorine molecule looks like this. Okay. So because the bond is non-polar, there's no net charge in the molecule. And we have learned in chemistry that any type of attractions between molecules, between atoms, are electrostatic in nature. So there must be some plus and some minus somewhere. But for non-polar molecules, where do they exist? Now, one thing to remember is that electrons, they are mobile. All right, they are electrons exist in electron clouds. They are forever moving. Remember, so at any point in time, if I take a snapshot of the chlorine molecule, there is a chance that we may have slightly more electrons on one chlorine than the other. Okay, slightly more, just a very, very small difference. So imagine that we have slightly more electrons on the chlorine on the right. So that chlorine would acquire a very, very tiny, slight negative charge. And the other chlorine atom would therefore acquire a negative charge. And what happens if you have another chlorine molecule nearby is this, that this slight negative charge on this particular chlorine atom, all right, because it has a slight negative charge, is going to repel the electrons in the nearby chlorine molecule as well. It's going to push the electrons in this direction. So what happens is now again the chlorine atom on the neighboring molecule on the left is going to have slightly less electron. This carbon atom is going to get slightly more electrons. So again, it sets up a small separation of charge. Now if you can see, there is a delta plus, there is a delta minus, there's a plus and a minus, so there's a weak interaction between these two non-polar molecules. Now we call this kind of phenomenon, or this kind of dipole, an induced dipole. Okay, because it's actually induced by neighboring molecules. Okay, so this kind of intermolecular force is called induced dipole interactions. Okay, ID interactions. It's also known as your dispersion forces. So whenever you see dispersion forces, it actually means your induced dipole interactions. Okay, now these induced dipole interactions are not very strong because remember the plus and the minus charge, they are not very pronounced. They are not very strong. Sorry, they are not very large. Okay, let's look at what happens or the interaction in samples with polar molecules. For example, hydrogen chloride. So when you have HCl molecule, now HCl already has a dipole moment. Okay, why? Because the bond is polar and then the whole molecule is actually polar. So it has a permanent dipole in the molecule. So the interaction between hydrogen chloride molecules would primarily be between these permanent dipoles. Okay, this is a permanent dipole. So this kind of interaction for polar molecules, we say that the intermolecular forces are PD. PD meaning permanent dipole interactions. Okay, and this permanent dipole interactions are stronger than your induced dipole interactions. Now, having said that, it's still very important to note this, that any molecule or any species that contains electrons, that has an electron cloud, would have induced dipole interactions. So polar do also have your ID interactions. Okay, just that because the PD interactions are so much stronger than the ID interactions, when we talk about polar molecules, we just mentioned that the dominant interaction is your PD interaction. Okay, but that doesn't mean that your induced dipole interactions are not there. When again any molecules that contains electrons or an electron cloud, there will definitely be some form of induced dipole because the electrons are consistently moving. So the electron cloud would distort and you will have some form of induced dipole interaction. So we have seen that there are different types of intermolecular forces. We have looked at dispersion, which is induced dipole. Once again, ID interactions exist between any species that has electrons. Okay, but it is the only intermolecular forces of attraction between non-polar molecules. Next, we also have something called dipole or permanent dipole interactions. These are the interactions that exist between polar molecules, and dipole interactions are stronger than your induced dipole interactions. Now, your induced dipole and permanent dipole interactions are collectively known as van der Waals forces of attraction. So for those of you who have heard this in the O levels, van der Waals essentially means either ID or PD. Now we will learn two more types of intermolecular forces. One of them is known as ion dipole interaction. So ion dipole interaction is the attraction or the electrostatic forces of attraction between an ion and a dipole. For example, if I have sodium ion dissolved in water, so what happens is that your sodium ion is actually interacting with the negative charge, the partial negative charge on your water molecule. Okay, so again, this is an electrostatic type of interaction. You have plus and minus. So this interaction is between an ion and a permanent dipole. So we call this an ion dipole interaction. Now, ion dipole interactions are important when we are discussing your enthalpy change of solution. Why do some ionic compounds dissolve in water and why do some ionic compounds not dissolve in water? It depends on this the strength of this ion dipole interaction. Okay, the last kind of intermolecular forces that we're going to learn is very important. It's called hydrogen bonding. Now, hydrogen bonding exists in molecules that contains hydrogen that's attached to a small and strongly electronegative atom. So if a molecule contains hydrogen that's attached to fluorine, oxygen or nitrogen, then that molecule will exhibit hydrogen bonding. Okay, so the famous 3 examples in the syllabus would be number 1, water, number 2, ammonia, and number 3, hydrogen fluoride. Okay, so right now we're going to see what exactly is hydrogen bonding. So when we have water, water looks like this. Recall that water, the bonds in water, they are actually polar. Okay, reason being oxygen is more strongly electronegative than hydrogen. So there is going to be a special type of interaction that occurs between the hydrogen that's bonded to FO or N and the lone pair, all right, the lone pair of electrons on the oxygen of a neighboring molecule. Okay, this interaction is called hydrogen bonding. Okay, why is hydrogen bonding so special? It's because hydrogen bonding is much stronger than your average PD-PD. Why is that so? When hydrogen is bonded to a small, strongly electronegative atom, remember the electrons will be put very, very close to oxygen. So the positive charge that is formed on your hydrogen is going to be quite large. So as a result, the interaction between this hydrogen and the lone pair, the pair of negatively charged electrons on the oxygen atom of a neighboring molecule is going to be very strong, and so much so that we name this strong interaction, we give it a special name, we call it hydrogen bonding. Now similarly, if you look at ammonia, ammonia has also hydrogen that's bonded to a small, strongly electronegative nitrogen atom. So the hydrogens carry a delta positive charge, and this delta positive charge would form an electrostatic attraction to the lone pair on the nitrogen atom of a neighboring ammonia molecule. Okay, and once again, this electrostatic attraction is very strong, and we give it a special name, we call it hydrogen bonding. The last example that we're going to look at would be hydrogen fluoride. Hydrogen fluoride has a hydrogen that's bonded to a small, strongly electronegative fluorine atom. So once again, the hydrogen atoms are going to carry a delta positive charge, and this delta positive charge can form a strong attraction to a lone pair on your fluorine atom of a neighboring hydrogen fluoride molecule. So once again, this attraction is very, very strong, and we give it a special name, we call it hydrogen bonding. Now, hydrogen bonding, as mentioned, is one of the strongest intermolecular forces of attraction. And why is that significant is because, for example, in O-levels, we have learned that simple molecules, they have low melting point and boiling points, so most of them exist as gases at room temperature. However, if you look at water, water is actually a liquid. That means that the intermolecular forces of attraction are a bit stronger than expected. So back then in O-levels, I used to tell my students that there's a special type of intermolecular forces between water molecules, and now we learn that this special type of intermolecular forces is known as hydrogen bonding. Now let us very quickly run through the type of intermolecular forces of attraction between these covalent compounds with simple molecular structures. So earlier we have already seen the structures of these molecules and whether they are polar or non-polar. So if you need a recap, please watch the video before this. Now, NO2 is actually a polar molecule, so it would have your dipole-dipole interaction or your PD-PD interactions. Water is the classic example for hydrogen bonding. CO2, because of the linear shape, it is actually non-polar, so you have your ID or your dispersion forces. Methane is a hydrocarbon. As mentioned, hydrocarbons are all non-polar, so you would have dispersion forces again. Ammonia is another example for hydrogen bonding. PF5, we have also seen, due to the highly symmetrical arrangement of atoms, is actually non-polar, so we have dispersion. And ClF3, if you look at the structure, there is a lone pair on the central atom. As mentioned before, if there's a lone pair on the central atom, the molecule is very, very likely to be polar. So we have PD-PD or dipole-dipole interactions. So finally, after going through the entire series of new concepts, we are finally able to discuss the factors that affect the strength of intermolecular forces between molecules. And there are two factors, molar mass and type of intermolecular force. We are going to look at it in greater detail in the subsequent slides. So when comparing two substances with simple molecular structures, it is very important to check first the relative molecular mass. Now, why is that important? Is because when a compound has a very large relative molecular mass, it would mean that it has a very, very large electron cloud. That means it has a lot of electrons. It has a huge electron cloud. And what happens when a compound has a large electron cloud? For example, let's say we have this compound with a large electron cloud, then it becomes more polarizable, meaning it can be distorted to a greater extent. Okay, so you can imagine this like a very fluffy pillow. The larger the pillow, the more you are able to distort the pillow. Distortion of electron cloud is called polarization. Okay, and the ability of the electron cloud to be distorted, the tendency of the electron cloud to be distorted is called polarizability. Okay, so a compound with a larger electron cloud means that it is more polarizable. And what happens when it's more polarizable is that you have greater separation of charges, okay, and then the extent of your dispersion forces would be even stronger as well. Okay, so much so that when you have a huge electron cloud, it is going to outweigh the different types of intermolecular forces. So earlier we mentioned that dipole-dipole interactions are stronger than your induced dipole, but when you have a huge electron cloud, it is going to override that factor that we were looking at. So once again, the very first thing to check when you are given two simple molecules is the relative molecular mass. If one of them has a much larger relative molecular mass, that substance or that compound is going to have higher melting point, boiling point than the other. Okay, the reason for that is because it has a larger electron cloud, it is more polarizable, therefore there will be stronger dispersion forces. Now, if the two substances that you compare have similar relative molecular masses, then you will encounter three possible scenarios. Okay, so assuming that we are comparing molecule A and molecule B, they both have similar relative molecular masses, then you will encounter three situations. One is where A is polar and B is also polar. Scenario number 2, A is polar, or one is polar, the other one is non-polar. And scenario 3, where both substances are non-polar. So we'll go on then to look at each scenario, how then we determine which substance would have stronger intermolecular forces. Now, in the first scenario where we compare two polar molecules of similar MR, the first thing to check is whether any of the substance can form hydrogen bonds. So if one of them can form hydrogen bonds, then the substance that can form hydrogen bond would have the stronger intermolecular forces of attraction, and therefore it would have the higher melting point, boiling point as well. Okay, why is that so? Because we have already mentioned that hydrogen bond is stronger than your average dipole-dipole interaction. So for example, if we compare between HF and HCl, both are your polar molecules. Their molar masses don't differ by a lot. Okay, so in this case, we need to look out for whether any one of them can exhibit hydrogen bonding. HF is capable of forming hydrogen bonds, therefore it would have the stronger intermolecular forces and therefore the higher melting point and boiling point. Now in the second case, where both molecules are capable of forming hydrogen bonds, then you need to compare something called the extent of hydrogen bonding, or the average number of hydrogen bonds that the substance can form between the molecules. Now what do I mean by that? Is that when you compare, for example, between water, hydrogen fluoride and ammonia, how do we find the average number of hydrogen bonds is this? Okay, to find the average number of hydrogen bonds that each substance can form, or each molecule can form, we need to look at two things. We need to look at, number one, the number of hydrogen atoms that are bonded to this small, strongly electronegative atom. Second thing that we need to look at is the number of lone pairs on this small, strongly electronegative atom. Okay, the average number of hydrogen bonds would be the smaller number of the two. What do I mean by that? So if we compare, if we look at water, water has two hydrogens that are bonded to oxygen. There are two lone pairs. So the average number of hydrogen bonds that water can form would also be two hydrogen bonds per water molecule. Now if we now look at hydrogen fluoride, hydrogen fluoride has one hydrogen bonded to fluorine, and fluorine actually has three lone pairs. Okay, so again, the average number of hydrogen bonds that hydrogen fluoride can form would be the smaller of the two number. So on average, your hydrogen fluoride can only form one hydrogen bonds between the molecules. And lastly, when we look at ammonia, ammonia has three hydrogen bonded to your nitrogen, but it only has one lone pair. So again, the average number of hydrogen bond would only be one. So when you compare between water and hydrogen fluoride as well as ammonia, you would find that water is capable of forming the most number of hydrogen bonds. Therefore, it would have the strongest intermolecular forces of the three, and then it would have the highest melting point and boiling point as well. Now if you want to go on further to even compare between HF and NH3, hydrogen fluoride and ammonia, how do we go on to compare, because they both on average can form one hydrogen bond? We can look at now the polarity of the bond. Because fluorine is more electronegative than nitrogen, so the HF bond is more polar than your NH bond. So you would expect the hydrogen bonds between hydrogen fluoride to be slightly stronger than that between your ammonia molecules. Okay, however, most of the time we don't go to that extent. It will stop at the extent of hydrogen bonds. Now, when we talk about extent of hydrogen bonds, we need to consider one more scenario, which is something called intra and inter-hydrogen bonding. Now, this is common when we look at organic compounds. So, let us now compare between the two organic molecules P and Q. So once again, the first thing that we check is the relative molecular mass. P and Q are actually isomers, so they have the same molecular formula, so they actually have the same molecular mass. So when comparing between two compounds of the same or similar molecular masses, we then look at which scenario it falls into. Both P and Q are actually polar. And so if both are polar, we need to then check for hydrogen bonding. Now, over here, if you look at molecule P and molecule Q, they both have this functional group, this hydroxyl functional group. They are alcohols. And in organic chemistry, when we look at your hydroxyl group, it is also capable of forming hydrogen bonds. Why is that so? Is because you have, again, a hydrogen bonded to a small, strongly electronegative oxygen atom. So all alcohols in your organic chemistry, they are capable of forming hydrogen bonding. Okay, so both P and Q are capable of forming hydrogen bonds. Now we need to look at the extent of hydrogen bonds. At a glance, it may seem like there's no difference. However, you need to be aware of something. When you have the hydroxyl groups in a 1-2 position, okay, the hydroxyl groups can be orientated in this particular fashion. Okay, and what's so special about that is now this hydrogen atom can form a hydrogen bond with the lone pair on the oxygen atom that is in the same molecule. Okay, so we call this an intramolecular hydrogen bond. Now, when a compound, when a molecule is capable of forming intramolecular hydrogen bonding, it means that it will form less intermolecular hydrogen bonding. Okay, and if the compound forms less intermolecular hydrogen bonding, it means that the intermolecular forces is going to be weaker. Okay, if you compare it to molecule P, now the two hydroxyl groups are further away, therefore the hydrogen atoms cannot interact well with the lone pairs on the oxygen atom because they are too far apart. Okay, in fact, these two hydroxyl groups are in a 1-3 position, so they are too far apart for any intramolecular hydrogen bonding. Therefore, molecule P, okay, would have more intermolecular forces of attraction, intermolecular hydrogen bonding, and therefore it would have stronger intermolecular forces. Now, a very quick analogy for this is that, for example, you have a friend who is very happy, who forms very strong bonds with himself. Okay, so he is very happy being alone. Okay, so is he going to have many friends? If he spends all the time with himself, the answer is he's not going to have a lot of friends. All right, so if he's not going to have a lot of friends, one day when he gets into trouble, or if someone wants to break him apart, is he going to find support from people? The answer is no. Okay, so that is the case for molecule Q. For molecule P, this friend is not capable of forming strong bonds with itself, so he relies on his friends. He goes around making many friends. So one day if he encounters some trouble and someone tries to break him, his friends will then come and support him because he has formed very strong friendship with many people. Okay, so again, the moral of story is this: if a molecule is capable of forming intramolecular hydrogen bonds, okay, that means that it will form lesser intermolecular or less extensive intermolecular hydrogen bonds. Therefore, the intermolecular forces will be slightly weaker. So in the second scenario, we're comparing two molecules of similar MR. One of them is polar, the other one is non-polar. Now this case is very, very straightforward. The polar compound will always have the stronger intermolecular forces of attraction and therefore the higher melting point, boiling point. Why is that so? Is because your dipole-dipole interaction is stronger than your dispersion forces when you have similar sized electron clouds. In the third scenario, we are comparing between two non-polar molecules of similar MR. Okay, this usually happens when we are looking at isomers. Okay, so the difference now must be due to surface area. Okay, so as mentioned, we have already learned in O-levels isomerism. For example, if you look at butane, okay, I'm not going to draw in the hydrogens, but this is the carbon skeleton for butane. Butane can exist in this isomer, which is your methyl propane. Okay, so if we were to analyze the electron cloud between the two molecules, butane would have an electron cloud that is something like this. Okay, and methyl propane, which contains a branch, would have a more spherical electron cloud. And how is that important is this? If you compare between two butane molecules, because of the more elongated electron cloud, it is capable of forming more extensive dispersion forces or dispersion interactions. Okay, as compared to your methyl propane, where it's slightly more spherical. Okay, so the extent of interaction between the electron cloud would be slightly less. Okay, so in this case, the straight chain isomer is going to have a higher or stronger intermolecular forces of attraction as compared to a branch chain isomer. Okay, reason for that again is due to the surface area, which will affect the extent of interaction between the molecules. Now in O-levels, we have learned that the structure and bonding of substances actually affects their physical properties, and we learn not just melting point and boiling point, but as well as solubility. Right? Back then we learned that ionic compounds are generally soluble in water, but not organic solvents, and covalent substances are generally soluble in organic solvents, but not water. But back then we didn't learn the reason why. So now that we have learned the different types of intermolecular forces, we can then understand better why certain substances can dissolve in water and certain substances cannot. So the rule goes something like this. If you are trying to dissolve substance A in substance B, for example, okay, so for solute A to be soluble, to dissolve in solvent B, these two criteria must be met, that the interaction between A and B must be stronger than or equally strong as your AA interaction, and your interaction between A and B must also be equally strong or even stronger than your BB interaction. Now what do I mean by that? Earlier in O-levels, we have learned that ethanol is actually soluble in water. Okay, this is unexpected for simple molecules because we have learned that simple molecules in general, they do not dissolve in water. So let's see why is that so. So ethanol is solute A, water is solvent B. Let's analyze the interaction between A and B. Okay, between ethanol and water. Remember, ethanol, alcohols are capable of forming hydrogen bonds as well. Okay, so A and B interaction in this case would be hydrogen bonds. Your interaction between your ethanol molecules is also hydrogen bonds, and your interaction between water molecules is also hydrogen bonds. So if you take a look whether the two conditions are met, hydrogen bonds between A and B are equally strong compared to the hydrogen bonds between A and A and also between B and B. Therefore, the interaction between A and B would release sufficient energy to actually overcome the interactions between AA and between BB. That's why ethanol is soluble in water. Now let's look at an opposite example. Okay, we also learned that alkanes, okay, for example, hexane, okay, C6H14, hexane is actually insoluble in water, or rather they do not mix, they are immiscible. Okay, so why is that? So again, let's treat hexane as solute A and water as solvent B. So AB interaction, what kind of interaction is this? I would say that it's intermediate between induced dipole, and permanent dipole. So in this case, we can just call it your van der Waals. Okay, the interaction between your hexane molecules again will be your dispersion or again van der Waals. And then between your water molecules, it is actually hydrogen bonding. So let's check the two conditions again. Your AB interaction, van der Waals, is compared to AA, it is equal, it is similar. But however, when you compare AB to BB, all right, is van der Waals stronger than your hydrogen bonding? The answer is no. All right, so the interactions between hexane and water, the van der Waals interaction, they do not release sufficient energy to overcome the strong hydrogen bonding between your water molecules. As a result, your hexane do not mix with water. So once again, we return to this table where we saw in the very first video, where we discussed the factors that affect metallic bonds, ionic bonds, and then also covalent bonds. Now we look at the factors that affect your intermolecular forces between simple molecules. Okay, so in this video we have seen that it depends on two things. We always check molar mass or relative molecular mass first, followed by the three scenarios where we have either both polar, one polar and one non-polar, and two non-polar molecules. So when you are given a question where you need to compare the physical properties between two substances, the very first thing that you need to do is to check what kind of substance they are. So for example, in some questions you will be comparing between an ionic compound versus a simple molecule. So in this case, it's very straightforward. You need to state the structure, you need to state the bonding. Okay. In general, any intramolecular bond, that means your metallic bond, your ionic bonds, and your covalent bonds, they are much stronger than your intermolecular forces of attraction. Okay, we have learned this in O levels as well, that your intermolecular forces are generally weak, so it doesn't require a lot of energy to overcome them. So if you are comparing between metal, ionic compound, or giant covalent compounds, they will definitely have stronger interactions, stronger attractions compared to simple molecules. So just to recap again, if you are comparing between two metals, then we can actually make use of this table. If you are comparing between two metals, then we just have to focus on this particular column in answering the question. So you will say that both metals have giant metallic lattice structure with strong metallic bonds, and then you go on to analyze the strength of your metallic bonds based on the two factors, number of valence electrons as well as your cation size. If you are comparing between two ionic compounds, again you can focus on this particular column. In your answer, you need to mention that both have giant ionic lattice structure with strong electrostatic forces of attraction between oppositely charged ions, and then you go on to analyze these factors, the charge of cation, charge of anion, and the interionic separation or interionic distance to determine which one has the stronger attraction between the two. Similarly, if you are comparing between covalent bonds, then you just have to mention that they have giant molecular structure with numerous or network of strong covalent bonds, and then you go on to analyze the atomic size of your atoms in the covalent bond.